In the previous chapters, we talked about the chemical equilibrium and also look specifically at the acid-base equilibrium. In chapter 19, we're going to look at the ionic equilibrium in aqueous systems. There are 4 topics in this chapter. We're going to go over the first 3. In chapter 19.1, we're going to look at how to make a buffer and also how does a buffer work. In 19.2, we're going to talk about the acid-base titration curves. So how to construct acid-base titration curve or how to use the acid-base titration curve to obtain useful information. In 19.3, we're going to talk about the solubility of ionic compounds. In chapter 19.1, we're going to look at acid and base buffers and know what it is and using the knowledge of equilibrium to understand how it works. And then we'll also talk about how to make a buffer. An acid-base buffer is a solution that lessens the impact on its pH from the addition of acid and base. So if you have a chemical reaction which you need to control the pH, you don't want the pH to change during the entire reaction. You're gonna need a buffer, right? So a buffer helps you, right, to maintain a certain range of pH, right? So even you add acid and base, right? So in this example, you see the picture on the top. So if you have a solution that is not a buffered solution, right? So at the beginning, you measure the pH using a pH meter, right? So the pH is 5. By adding just 1 milliliter of this 1 molar hydrochloric acid, you see because the addition of the proton, the pH drops to 2. Right? So from pH 5 to 2, that means the change of concentration of proton by 1,000 times. Right? Because pH is the exponent when you're talking about the concentration of proton. Right? So if it is changed by 3, that's 10 to the third. So the concentration of the proton increased by 1,000 times. And if you add a base 1 milliliter of 1 molar sodium hydroxide, the pH, right, increase to 12. Right, so that means you have POH equal to 2, which is 14 minus 12. Right, so that means you have 0.01 molar of hydroxide. Right, so you can see by adding just 1 milliliter of this strong acid and the strong base, the pH changed significantly. However, in the second case, if you have a buffered solution, right, meaning that you have the same solution but now you're adding this buffer inside, so you're starting with the same initial pH and adding the same amount of acid, the pH only drops slightly, right? So from 5 to 4.98. And then if you add the same amount of base, it only increased by 0.02. Right, so now you can see how well this buffer works and how does the buffer helps prevent the change of pH, right, when you add the acid and base. So now you may wonder, how does a buffer work, right? So why the buffer can avoid the change of a pH, or not say avoid, but lessen the impact of a pH from the addition of acid and base. So the buffer works through an effect called common eye effect. Right, so for example, if you have acetic acid, right, when you dissolve acetic acid in water, because it's weak acid with a very low pKa value, so it only partially dissociate, right? So it generates a little bit proton and also is a conjugated base. Right, so but if you add a sodium acetate, right? So instead of adding the acid, you're adding a salt. So this ionic compound will completely dissociate, right? So you have this one-sided arrow. Right, so the sodium is gonna be the spectator ion, which will not be involved in the reaction. So the amount of this conjugated base, right? So the acetate here is equal to the concentration of this salt you added. Let's say if you have a mixture of this two, right? So you add acetic acid and the sodium acetate. Now you're creating a buffer, right? So because for these two type of compounds, they have a common ion, which is acetate. Right? So the acetate is the common ion. And we will explain how does this common ion can reduce the impact of the pH. So before we do that, let's look at this table first. Right? So if you have a mixture of acetic acid only, and without adding any of this acetate, right? So normally a acetate salt, right? So you see 1.3% of this acetic acid is gonna dissociate, right? Generating this amount of proton, and the corresponding pH is 2.89. So now you didn't add any of this acetate ion into the acetic acid, right? So although the acetic acid can generate some a little bit acetate, right? But that's not enough to show this common ion effect. In the second row, you start to add 0.5 molar of this acetate ion, right, which is about half of the concentration of the acetic acid. Now, because you're adding the acetate, right? So you're basically increasing the concentration of the acetate in the first direction. Right, so based on what we learned in chapter 18, that will shift the chemical equilibrium to the left. Right, so that means that will decrease the percentage of the dissociation of this acetic acid. So we're gonna have only 0.036% of dissociation. That means a much lower concentration of proton generated from the dissociation. So the lower the proton concentration, the higher the pH. Right? So by adding 0.05 molar of this acetate ion, right, the pH increased to 4.44. In the third row, you're adding the same concentration of acetic acid and the acetate. So now your concentration of the acetate is even higher. So that will further push the equilibrium position to the left, meaning that even less amount of the proton will be generated, and the pH will increase. Right, in the last row, you increase the concentration of acetate to 0.15 molar, which is even higher than the concentration of the acid. Again, that will even push the equilibrium position to the left, right? So same deal, less percent dissociation, less proton generated, and a higher pH. But you can see that other than the first row, right? So if you look at the second, third, and fourth row, although their concentration differs, right? But the change of pH is not very significant compared to the first row. Right, so meaning that when you have this common ion, right, with a pretty good relative concentration, right, meaning that their concentration not too different, right, you can see the change of pH become very small. So that's what it means by the common ion effect. In the previous slides, you see the impact of a common ion effect on the pH. Right, so once you start to add acetate into acetic acid, the change of pH become very small. Right, so the pH is the native log of proton concentration. Right, so to see the impact of a pH, we need to look at what happens to the proton concentration. So for acetic acid, when it dissociates and generate proton and acetate, the percent of dissociation or the amount of the proton generated, it highly depends on the relative concentration or the ratio of the acetic acid and the acetate, right? For this conjugated acid-base pair. For this equation, we can express Ka, right, using this equation. And because we want to see the impact of pH, which is the native log of a proton concentration, so you want to highlight the proton concentration. So by rewriting this equation on the left, we can derive that the proton concentration, right, is equal to Ka, which is the dissociation constant for acetic acid, which is a constant, right? So this is a constant value, and multiply the ratio of the acetic acid concentration divided by the acetate concentration, right? So it's the acid and the conjugated base, right? So because Ka is a constant, so the proton concentration will depend on the ratio of the acid and the conjugated base, right? So we can draw two conclusions, right? So based on this equation, that first, if the ratio goes up, right? So if this ratio goes up and the Ka is a constant, that means the proton concentration will also goes up. And when the proton concentration goes up, the pH will goes down, right? So we can add that the pH is gonna goes down, right? So on the other end, if we decrease or lower the ratio, right? If we lower this ratio, the concentration of proton will decrease, right? So in that case, the pH will goes up, right? So if we maintain this buffer system at the same temperature, which means the Ka is constant, right? So the pH will depend on the ratio of the acetic acid and the acetate. So that is a very important concept, right, related to the preparation of a buffer, right? So that's not the only important thing, but it's one of the most important concepts regarding preparing a buffer, right? So because you are adding this acid and the salt, right, has this common ion, and you can determine the relative ratio, because the relative ratio will determine the final pH of the buffer. This figure further explains the conclusion we draw from the previous slides. Right, so we're gonna see how does the buffer, right, impact the change of pH, right, when acid and base are added. Right, so we still have this same equation here. Right, so we wanna see the impact on the proton concentration, which is also the pH, from the ratio of the acid and the base. So in the figure in the middle, we have an equal concentration of the acid and the conjugated base. Right, so meaning it's a 1-to-1 ratio. Right, so it's a 1-to-1 ratio. So the term in this circle is equal to 1. Right, so that in that case, the proton concentration is equal to the Ka value, or the pH is equal to the pKa of the acid. So if we move from the middle to the left, right, so we're adding some of this proton, right, so by adding some strong acid. So when you add strong acid, right, into this buffer, this proton, right, because strong acid completely dissociate, right, so this proton that you added from the strong acid will completely react with the base, which is the acetate. Right, so the acetate here, originally in the buffer, will react with the proton added, and generating acetic acid, and water. So in terms of their concentration, because you consume some of the acetate and generate some of the acetic acid, so the acetic acid concentration goes up and the concentration of the acetate goes down, and this dashed line matches the original concentration. Right, so now you no longer have a 1-to-1 ratio, right? So you have a higher concentration of the acid, which is the numerator. Right, so in this case, the ratio is going to be higher than 1, right? Because your numerator is higher than the denominator. So the proton concentration in this system is going to increase, right? So increasing proton concentration meaning the pH will be dropped a little bit, right? So for this one, the pH is gonna decrease, right? It's decreased slightly because the change of this ratio is also very slight. So what if we move from left to right by adding base, right? So by adding a strong base, for example, sodium hydroxide, right? Because strong base also completely dissociate. So this hydroxide added, right? It will equal to the amount of base added, and this hydroxide will react completely with the acetic acid, right? Because the base react with the acid. So this is the original concentration of the acetic acid in the middle, and now you're adding a hydroxide, they will react and generating the acetate. And so now you are having a higher concentration of acetate, and because you consume some of the acetic acid, so its concentration decrease. So now this ratio become less than 1, right? Because you have a smaller concentration of the acetic acid, which is the numerator. So this ratio is less than 1. The proton concentration, right, compared to the scenario in the middle, will become smaller. So the pH will increase. Let's work on an example problem. In this question, we have prepared buffer solution that contains 0.5 molar of HClO, which is the hypochlorous acid, and that's not enough, right? Because we also need a salt that contains the same ion, the common ion. So we have this sodium hypochlorite. So we can list the ICE table, right? So to figure out what happens to the concentration after we mix them. The K value is given here, so it's a very small number, 10 to the negative 8. So we can use this to make some assumptions. Right, so first we have this chemical reaction. So the hypochlorous acid, right, dissociate in water, generating this hypochlorite ion and the proton. So the starting concentration of these two are given, right? So the hypochlorous acid is 0.5. Because this NaClO is a salt, right? It completely dissolved. So the concentration of this ion, this anion, is also equal to the concentration of the salt you added. So that's the starting concentration, 0.6. Right, so we can use X to indicate the change, again, of the coefficient equal to 1. So for the product, we have positive X, and for the reactant, we have negative X. And because this K value is very small, so we can say that compared to 0.5 or 0.6, the magnitude of this X is negligible. So instead of using 0.5 minus X or 0.6 plus X, we just use 0.5 and 0.6 in our calculation. Right, so to calculate X, we can express the Ka, right? So Ka equal to the concentration terms of the product divided by the reactant, and we then rewrite the equation by taking the proton concentration out, right? So the proton concentration equal to Ka multiply the ratio of the acid and the conjugated base. Right, so Ka is already given, and based on our assumptions earlier, we can use 0.5 and 0.6 directly to represent their equilibrium concentration. But if you want to use 0.5 minus X and 0.6 plus X, that's also fine, but you're gonna find out you're gonna get a very similar result. Right, so by doing the calculation, we find out the proton concentration is 2 times 2.4 times 10 to the negative 8. And you can validate it, right? So justify your assumption, because this percentage is like way less than 5%, right? So the assumption we made is our good one. And if we know the proton concentration, we can get the pH, right? So the pH is about 7.62, right? So meaning that, so part A, right? So after mixing them, this buffer will have a pH of 7.62. So part B asks you what happens to the pH, right, after adding 0.02 moles of a solid NaOH into 1 liter of the buffer solution. So for part 2, first we're gonna figure out the concentration of the hydroxide, right? So the question tells you the number of moles added and the volume. So we can use number of moles divided by the volume to calculate the molarity. Right? So we're adding 0.02 molar of hydroxide. Because the hydroxide comes from the sodium hydroxide, which is a strong base, right? So 100% of the hydroxide will be dissolved in water, and that will react with the acid that in the buffer. Right? So because you start with 0.5 molar of this acid, right, by adding 0.02 molar of hydroxide, so this reaction is a one-sided reaction, right? Because this is a strong base, right? So it will go to completion. So the amount of the acid, right, decreased will be 0.5 minus 0.02, right? So because 0.02 molar of the acid is consumed by 0.02 molar of the hydroxide. So the final concentration of the acid after adding the base become 0.48. And because you also generate some of this acetate, right? So the acetate concentration, initial concentration 0.6, and then it increased to 0.62. Right, so we're gonna use this equation, mean concentration, right, yeah, as the initial concentration in our ICE table next. Right, so then we consider this equilibrium equation. Right, so using the concentration we calculated from the previous step. Right, so this is a case that the added hydroxide already reacted. Right, so we can use the same approach, using X to indicate the change of concentration. So this will be the equilibrium concentrations, right, for the concentration terms in the expression of Ka. So we can use the same approach we used in part A, right? So ignore the X, right, because they're relatively small compared to for 0.48 and 0.62. Right, so apply the same equation here. So we can use this number directly based on our assumption, right? So we calculate the proton concentration is going to be equal to 2.2 times 10 to the negative 8. And also, again, right, here I didn't do it, but you can also justify it, right, your assumption, right? You can divide this concentration by 0.48 and 0.62, and the percentage is way less than 5%, right? So that means our assumptions are valid. Then you can convert this proton concentration into pH. Right, so now adding 0.02 molar of hydroxide, the pH only increased from 7.62 to 7.66. So to conclude what we just learned, right, so we can look at the figure on top. So this diagram gives you a very good idea about what happens, right, to the pH when the relative ratio of the acid and its conjugated base changed. Right, so if you have a buffer system, right, so if you add a strong acid, that strong acid will consume some of the conjugated base, right? So that will increase the concentration of the acid, decrease the concentration of the conjugated base. So that will increase the ratio. Right? Increasing the ratio meaning increasing the proton concentration, so the pH is gonna be smaller. Right, so for the opposite direction, right, when you add the base, that base will react with the acid that already exists in the buffer. So that will decrease the concentration of the acid, but increase the concentration of the conjugated base. Right, so this ratio is going to be smaller, and the proton concentrations also become smaller, so the pH will increase. So later, scientists developed this Henderson-Hasselbalch equation. Right, so that equation is derived based on this equation that we already know. Right, so based on this equation, if we take the negative log of both sides, right? So remember, negative log can be represented by a lowercase p, right? So p of something means the negative log of something, right? So if we take the negative log of both sides, the negative log of proton concentration is pH, right? So that will be pH, and the negative log of Ka is pKa. Right, so when you take the negative log of A times B, so A times B, that will equal to the negative log of A minus the negative log of B. Right, so here A is the Ka value, right? So here we have negative log of Ka value, which is pKa, and what's left is minus negative log of B. So B is the ratio of their concentration, right? So overall, we have this pH equal to pKa minus log of acid concentration divided by the base concentration. And we can further, right, rewrite this equation by changing the sign here. So when you have a negative log A over B, that is equal to positive log B over A. Right, so here, when you turn this negative sign into positive, here you have to flip the numerator and denominator. Right, so at the end, the Henderson-Hasselbalch equation is pH equal to pKa plus, right? So plus log concentration, log ratio of base divided by the acid, right? So in the previous form, we have acid over base, but by changing the sign in front of the log, we have base over acid. Actually, you can use both forms, but commonly people use this equation, right? So meaning that if we know the pKa or the Ka of an acid, right, because those are constant at a certain temperature, right? So we can take the negative log of the Ka value to get the pKa. So this is pretty much known, right? So if we know how much base and acid we add in this buffered solution, right? So again, this base and acid must contain these common ions. We can calculate pH directly using this equation. So if we look at the same problem we did earlier, right, for part B, so after we add 0.02 molar hydroxide, we have the concentration of the acid and the base. Right, so other than using the ICE table, we can apply this equation directly. Right, so this is the pH equal to pKa plus log base over acid. Right, so if we have plus, that's base over acid. pKa value is the negative log of this Ka, and so that will be 7.54, and we know the concentration of the base and the acid, so we got 7.65. So using the ICE approach, we got 7.66. right? So almost identical result, but the math become much easier. Now we have looked at how does a buffer works, right? And how does it respond to the addition of the acid and the base. So now let's look at another two important parameters about a buffer. Those two important parameters are buffer capacity and buffer range. First, let's take a look at a buffer capacity. Buffer capacity is a measure of the strength of a buffer, which is its ability to maintain the pH following the addition of strong acid and the base. So basically, how long does this buffer is gonna insist, right, to avoid this significant change of pH when you keep adding the acid and the base. So in this figure, we have a initial condition. So we have a buffer that has an initial pH of 4.74, right? So actually, you can get this same initial pH by using different mixing recipes. So if you mix 1 molar of this acetic acid and 1 molar of this acetate salt, you get pH 4.74. But if you mix them with 0.3 molar of acetic acid and 0.3 molar of acetate salt, the initial pH is still 4.74, right? So the buffer pH, the initial pH is independent of the capacity, right? Meaning that as long as you have the same ratio, right, the pH is going to be the same, right? So it doesn't matter the absolute concentration of the component of the buffer, right? So in this figure, we have 4 buffers systems, right? So they have the same initial pH because they have the same ratio of the acid over base, but they have different capacity because the absolute concentration of the component added are different, right? So the highest is 1.0 molar, meaning that you have a 1.0 molar of acid and the base mixed together, and the one with the lowest capacity, you only have 0.03 molar of each, right? So now let's see what happens, right, if we add a base into this acid buffer. So if the absolute concentration is 1.0 molar, right, so that means the initial concentration of the acid and base are all equal to 1.0 molar. The addition of a base only slightly increase the pH, right? The pH only increase slightly, and that's because for this buffer, its buffer capacity is big or high, right? Or it has a higher strength to avoid this change of pH, right? So, but for this buffer number 4, which is the one with the lowest capacity, when you add the same amount of the base as you did in the first case, the pH increased, right, all the way to above 5.05, right? So the change of pH is bigger, and that's because your buffer is weaker, or the buffer strength is lower, or we can also say the capacity is lower, right? So now comes to a question about how do we prepare this buffer, right? So that it really depends, right? So it really depends on your chemical reaction or your system, or what you're gonna add, and what's the concentration of the acid and base you're gonna add, right? So if I'm dealing with an experiment that use very low concentration of the reactant, maybe a capacity of 0.03 molar is big enough, right? But if I need to add some acid and base, or I'm dealing with a reactant with concentration that gonna generate some acid and base that gonna be higher than this 0.03 molar, that means this buffer will not be strong enough, right, or is not qualified as a good buffer for that system. That means you're gonna need a buffer that has a much higher, right, capacity, so the pH can be maintained. From the previous slide, we see that by increasing the absolute concentration of the component of the buffer, the buffer capacity can increase. And so in that example, we have the same concentration of a acid and base. And so the relative concentration of this acid base can also affect the buffer capacity. Right, so the general conclusion is that in terms of the relative concentrations, the closer the component or concentration are to each other, the greater the capacity. Meaning that if the acid and base have an equal concentration, the capacity is going to be the highest. Right? So the more different or more far away the concentrations are, the weaker the capacity of the buffer. So in this slide, let's look at a couple examples. So we have a two buffer system, right? So they have a different relative concentration of the acid and base. So for the one on the left, so you have a same concentration of acid and base, right? So the ratio, initial ratio is equal to 1. By adding a little bit amount of the strong base, so in this case by adding 0.01 molar of the hydroxide from a strong base, the base concentration increased by 0.01 and the acid concentration decreased by 0.01. Right, so the ratio after adding the base is 1.02. Right, you can see the percent change in terms of the ratio is only 2%. Right, so that's when you have the same concentration of acid and base at the beginning. Right, so in the second example on the right, right, so you have a 0.25 molar of acid and 1.75 molar of the base. Right, so if you look closely, if you add these two concentrations together, that's equal to 2, right? So which is also the total concentration of the acid and base. Right, so you basically have the same absolute concentration for the total concentration of acid and base, right? But you have a different relative concentrations now because they're no longer equal, right? So the concentration of the base is 7 times of the concentration of the acid, right? So by adding the same amount of the strong base, right, in the system, and the ratio becomes 7.33, right? So the relative percent change, right, from 7.33 from 7 to 7.33, you increase by 4.7%. Right, so let's look at this two system again, right? So if you have the equal concentration of the acid and base, by adding a little bit base, strong base, the ratio only increase by 2%. Right? But if you have a different concentration of acid and base at the beginning, right, with this high ratio, or this ratio that far away from equal to 1, by adding the same amount of base, the percent of this acid-base ratio increased by 4.7. So meaning that by adding the same amount of the base, the pH in the second buffer, it will be changed more than the pH change in the first buffer. Right, so that's why we said a buffer will have the highest capacity, right, when the component concentration are equal at a relative absolute concentration. Right, so to explain this conclusion using equations, we can say that using this equation, right, we derived in the previous slide, when the concentration of the acid and the base are equal, so this is log 1 equal to 0. Right, so the pH is equal to the pKa of the acid. Right, so we say that a buffer whose pH is equal to or near the pKa of its acid component has the highest capacity of a given concentration. So that means when you try to decide what type of buffer you want to use for your system, it depends on the pKa of the acid and the ideal pH you want to use, right? So say if you want to run this experiment, but I want to run it at a pH equal to say 5, right? So you want to find a weak acid whose pKa value is equal or very close to 5, right? Because that acid and the base, right? So that buffer you made with that acid is gonna have the highest capacity, which will act like a best buffer. The buffer range of the buffer is another very important factor to be considered when you try to determine what type of buffer you want to use. Right, the buffer range is the pH range over which the buffer is effective, and is also related to the relative buffer component concentration. Right, so the further the concentration ratio is from 1, the less effective the buffer, or the lower the buffer capacity. Right, so again, you want the ratio of this acid and base to be close to 1. And the buffer range, right, is the pH range where that buffer is still effective. Right, so if the buffer has a working range between 5 and 7, right, meaning that as long as your system are within this pH, the addition of acid and base will not change the pH significantly. Right, but if it is out of this buffer range, the buffer will no longer work. Right, so for example, if you have a buffer with a ratio of base over acid equal to 10, right, so by calculating the pH, that's going to be equal to the pKa plus log 10 equal to 1, right? So your pH is going to be 1 more than the pKa. And if you have a ratio of 0.1, the pH is going to be pKa minus 1, right? So it's going to be 1 less than pKa. So the buffer, normally the buffer range is plus or minus 1 the pKa value of the acid component in the buffer. Right, so meaning that you cannot pick an acid whose pKa are too far away from the desirable pH you want to use. Right, if you want to pick pH 5, you're gonna pick an acid that has a pKa, right, between 4 and 6. Right, the closer it is to 5, the better. So now let's conclude about how to prepare buffer and what need to be paid attention. Right, so first step, you're gonna choose the conjugated acid-base pair. And so we want the pKa of the acid close to the desired pH, right? Because the closer, the better, because the capacity under the buffer range. And at the same time, you don't want the component of your buffer to react with any other thing in your chemical reaction, right? So you don't want the buffer to interfere with your chemical reaction. And the second step is to calculate the ratio of the buffer component, right? So sometimes you cannot find the acid that has the exact same pKa value that matches the pH you want, right? So you can actually adjust it by changing the ratio of the acid base a little bit. And we already talked about how to do that in the previous example problems, right? So you can actually adjust the ratio of the acid and base you add a little bit to achieve the target pH. And the number 3 is determine the buffer concentration, right? So that's the absolute concentration. So again, that depends on your experiments, right? So if your experiments dealing with high concentration of reactants, you want a buffer with also high absolute concentration. Right, but for the most of the lab cell applications, we normally use 0.5, right? 0.5 is the way enough, right? Or even lower, right? And for number 4 is after you determine what to use, you calculate the amount you're gonna use. You're just gonna measure them out and then mix the solution. So after mixing the solutions, you're gonna check the resulting pH, like because everything you calculate is based on theories, right? So those are the theoretical values. And when you actually performing it and making it, there might be some human errors, right? So you always want to check the final pH after you mix them. And if it's close enough, that's okay, but if it's off, you have to add strong acid and base to adjust it. So there will be 2 homework problems regarding the pH buffers. Alright, so I'll see you guys in the next lecture.